Hello. So in today's lecture, we're going to be looking at vector spaces and vector spaces in general. Later on, we will look at specific vector spaces and how we use them in quantum mechanics. Okay, so we begin with the definition of a vector space. So definition. A vector space is a set we usually call V for vector space, together with two operations called vector addition and the other one is scalar multiplication. Okay, so what are these two operations? The first one, vector addition, is a map or an operation that takes two vectors. So it's a map from the Cartesian product V cross V back into V. So it takes two vectors and essentially adds them together to make another vector. Okay, so we can take V1, which we write with a little bar at the top just to show that it's a vector. And we take V2. Okay, both of these are from V. And we send them to V1 plus V2, which is again an element of V. Okay, so usually with maps, we write the name of the map in front, like f of xy. But here we put it in the middle because we treat it more as an operation, like you would with plus, minus, times, divide, and so on, rather than a function. Okay, but it is defined as a function or as a map. Okay, so that's the addition and scalar multiplication. This is a map between some underlying field. You don't have to worry too much about what a field is now. So we will be taking it either as the set of real numbers or the set of complex numbers. Okay, so in general, we will take the set of complex numbers as the field cross V, and then this maps into V. Okay, so how does this map work? Well, we take a complex number, let's say K, and we take a vector V, and we send them to K times V. And this is again an element of our vector space V. Okay, so K we call the scalar, and we do this scalar multiplication. Okay, so these two operations have certain properties that they need to satisfy, and we can write them as CANI or CANI and ADDU or ADU. So you can remember it like that, CANI and ADU. So what do these mean? So the C is for commutativity. Okay, so this means that if we take a vector vector V plus a vector U, this is the same thing as the vector U plus the vector V. So like addition and multiplication with real numbers is associative. Not associative, commutative. So you can do x plus y or y plus x, it doesn't matter. We have the same property here. So the next one is associative, which means if we take V plus U plus W, so if we do the U plus W first, because remember it's a binary operation, you can only do one thing at a time here. So U and W, we can operate them together, and then V and the net result, we can operate them together. Okay, what associativity says is that it doesn't matter in which order we do it. So we can do U plus W first, and then add it to V, or we can do V plus U, and then add it to W. Okay, it shouldn't matter which order we do it in. Okay, so that's associative. N stands for neutral element. Okay, so what this property says is that there exists a neutral element we call 0 from the vector space V, such that if we take any vector V plus this neutral element or plus the 0 element or 0 vector, it's got a few names, then this just gives us back the vector itself. Okay, so we call it neutral because it's not doing anything to the vector. Okay, so V plus the 0 vector is again V. Okay, and then we will show later on in the homework that this neutral element is in fact unique. So we can just give it the symbol 0. Okay, it's not like we have two neutral elements to worry about. Okay, and then lastly, I, that is the inverse element. Okay, so for all vectors V in the vector space, there exists a unique inverse we call minus V, such that V plus this minus V is equal to the neutral element. So they cancel each other out to give us back the neutral element. Okay, and again, we will show this for homework, that this minus V or this inverse is unique. Okay, so we write there exists with the exclamation mark. That just means there exists a unique. We can also write this for the previous statement, there exists a unique natural element. Yeah, and you will prove that later on. Yeah, so these are all the properties for the addition, the Caney part. Then the addu part relates the scalar multiplication with the addition on the vector space, as well as the multiplication and addition on the field, this complex numbers here. Okay, so the first one is associative. So there's Caney, so associative. Okay, so what this means is that if you have A, B times V, like this, then we can see that this B times V, that's the scalar multiplication. And then we have the A times the result, which is also scalar multiplication. Now, it shouldn't matter in which order we scale the vector. So we can do AB times V. Okay, where the product between AB is the product on complex numbers, and then the product between that result and V, that is the scalar multiplication product. So you need to be careful which product you're dealing with based on the elements on either side. So if you've got the product between two scalars, then it's just your complex multiplication. If your product is between a scalar and a vector, then it's the scalar multiplication. Yeah, so just be a bit careful about what you're dealing with. Okay, next one is distributivity. Okay, so there's two distributivities because there are two types of addition that we're dealing with. There's the addition between the vectors, the vector addition, and there's the addition between the complex numbers. And we want them to play nice with each other. So if we have A plus B times V, then we should have this distributivity between the two scalars and the vector. So then that would be A times V plus B times V. So we see that this addition on the left-hand side was between scalars. So that's the addition between complex numbers. And then on the right-hand side, the addition now becomes addition between vectors, because the A times V and the B times V, those are both vectors. So we see how they are playing nice with each other. Okay, then we have the other distributivity. Okay, so then that is when we have A and then V plus W, for example, then the scalar multiplication distributes over the vector addition. So then we have A times V plus A times W. Okay, so notice in this case, on the left-hand side, the addition was between vectors, and on the right-hand side, the addition is also between vectors. Okay, so it is different to the previous distributivity. Okay, And then last one, the U, that stands for unit. So this just means that out of this underlying field, in this case, the complex numbers, there is a unit. So there exists a unique unit we call 1. Okay, so in terms of the complex numbers, that's the standard 1. Okay, such that 1 times the vector is just the vector. So if you scale by a unit amount, then you're not really scaling at all, so we should get back the vector. Okay, so these are all the properties or axioms of a general vector space. Okay, so we won't be looking too much into general vector spaces because we have concrete examples that we're going to be working with. But just as a first example, let's look at the vector space constructed from R3. Okay, so example 1. Okay, so we choose our set V to be R3. So remember what that is. That is the set of X, Y, Z, such that X, Y, Z are real numbers. Okay, so it's the 3 tuples of real numbers. Now that's just the set. Okay, so there's nothing too special about that. To turn it into a vector space, we need to define the addition and the scalar multiplication. So we define the addition. So let's take 2 elements and show what happens when we add them. So if we take the elements x, y, z, the elements x, y, z plus elements a, b, c, how should we add these together? Now you can come up with your own way of adding them, as long as it's consistent with the above rules here. But the general method is to do element-wise. So x plus a, y plus b, z plus c. Okay, so that is the addition between real numbers. And just a quick note, since we are doing the addition between real numbers, remember the addition between real numbers is associative, commutative, and so on. So those properties from the real numbers gets inherited to this plus or this vector addition here. Yeah, and I'm going to leave that for homework to show that this satisfies those properties, the Caney and Adu. Okay, and then we can define the scalar multiplication. Similar way, we're going to take a complex number k, scalar multiply x, y, z. Okay, and then this is going to be defined as kx, ky, and kz. Okay, so you should have seen this in your previous math module. Okay, and then this vector space, this set V together with these 2 operations forms a vector space. Okay, so just as a little bit of homework. Show that this is a vector space. By showing that it satisfies the above rules. Okay. So show that this concrete example of a vector space is indeed a vector space. Okay. And then some extra homework on general vector spaces. Show that the neutral element is unique. So that's the 0. So just as a hint, when you're trying to show that something is unique, we can assume that there are more than 1. So assume that there's 2. So we have neutral element number 1, neutral element number 2, and then through your proof, you will show that they are actually equal. Okay, which means that there should only be 1. Yes, and then secondly, show that the inverse of a vector is also unique. Okay, so this is very short proof just to get you going with the idea of proving things. Later on, we will see that there are a few more proofs that we need to go through, but they will follow the same sort of structure. So if we're trying to prove something is unique, then it follows the same sort of structure as these two proofs over here. Okay, but these are some good small proofs just to go through now. Okay, and then just a note on this R3 vector space. So please revise the things you learned. No, sorry. In the previous math module. Okay, so that's your Maths 140 that you did last semester. Okay, so all of that stuff that you learned with the R3 vector space and the cross product, inner product, and so on that we added onto that vector space, please go over that as well. Okay, so we got a few more definitions to go through with this idea of vector space. And the first one is the definition for a subvector space or a vector subspace. Okay, so definition. A vector subspace. Okay, you might hear as well subvector space. Or you might hear linear subspace. Okay, and sometimes you just hear subspace. Okay, so since we're going to be dealing with vector spaces as our algebraic structure, we're not going to worry too much about differentiating between vector space and subspace. Okay, so we're only going to be working with vector spaces. So if we say subspace, we know we mean subspace to a vector space. Okay, so what is this? So a vector subspace is a subset of the set. So a set W, which is a subset of V. That is also a vector space. Okay, so we take our original set V, so from our original vector space, we pick a particular subset of elements, and if those subsets, if that subset of elements forms its own vector space, okay, so like independently, it's its own vector space, then we call it a vector subspace. Okay, so let's look at an example. So just a quick example to illustrate this idea. Let's say we have the vector space R3 as we constructed above, and we're going to take a particular subset. So we're going to choose particular elements from V to form a set W. Okay, so this is going to be the set X, Y, 0, such that X, Y are real numbers. And this is clearly a subset of V. But we know it's a subset, but is it a subspace? Okay, so we need to show that. So we know it's a subset. To show that it is a vector space on its own, we need to show these above operations here. Okay, so the plus operation, that needs to be satisfied. In other words, if you take any two vectors from W and you add them together, you should end up back inside W. And if you take a scalar times a vector from W, you should end up back in W. Okay, so we call that closure. Okay, because it's like a closed vector space on its own. Any operations you do in the space remain in the space, so it's closed. Okay, these other operations, the Caney and the Adu, those properties there, those will be inherited from the operation. So if you look at the subset and you keep the same operation, then of course it's going to satisfy those properties. So we just need to check this closure here. Okay, and before we start, it's important that this W is non-zero. Okay, so we can't do any work with it if there's no elements inside. Okay, so firstly, W is non-zero, so non-empty, sorry, so that's fine. Because if we choose X and Y to be 0, then we get the element 0, 0, 0, which is inside W. And in fact, the 0, 0, 0, if you remember from your Math 140, that is the 0 vector, or the neutral element. Okay, so it's non-empty. So let's show the closure under addition. So we're going to take two arbitrary elements from W, add them together, and show that it's again in W. Okay, so let's pick one. So W1 is an element from W, which means we can write it as W1 is going to be X1, Y1, and 0. Okay, W2 is from W, so we can write W2 as X2, Y2, and 0. Now, if we add them together, it should satisfy the condition to be inside W. So let's check that. W1 plus W2 is going to be this X1, Y1, 0 plus X2, Y2, and 0. If we add them together, we're going to get X1 plus X2. By the definition that we mentioned above, we're going to get Y1 plus Y2, again from the definition, and 0 plus 0, that's just 0. Now, X1 plus X2, we can just call that something like X3. Y1 plus Y2, we can call that something Y3, and 0, it's just 0. But this element here, X3, Y3, 0, is precisely the form of an element in W. You've got a real number, another real number, and 0. That's exactly what we've got here. So this must be in W. And since we started with two arbitrary elements from W, we ended up with an element from W. That means it's closed under vector addition. Okay, number 3, let's show that it is closed under scalar multiplication. So we choose some K from the complex numbers. We choose some W to be X, Y, 0s. This is from W. And we just check, is the product or the scalar multiplied version, is that in W as well? So K times W, that's going to be K times X, Y, 0. And this is Kx, Ky, and then K times 0, that's just 0. Okay, but again, this satisfies the condition to be inside W because Kx, that's inside here. Oh, sorry. Sorry, that's supposed to be C. Sorry, and then this was supposed to be C as well. Sorry, so we're dealing with C3 as the vector space. So it's very similar to R3. It has the same addition and scalar multiplication operations, but we're dealing with complex numbers instead. So the vector space is C3, and we take XY from C as well. Okay, so here we have Kx times Ky. Those are both complex numbers. 0 is just 0. So this is again an element from W. Okay, so it's closed under addition, it's closed under scalar multiplication, it's non-empty. So W is indeed a subspace. Okay. So that is the general method that you should follow when proving something is a subspace. Okay, so just another homework problem. Okay, so let V be R3. Okay, so not C3 this time, so it's R3. And W is going to be X, Y, Z, so that tuple, such that X plus Y is equal to Z. Okay, so that is the condition that we're using to choose the elements. We only choose the elements such that the first component plus the second component is equal to the third component. Yeah, and then the homework is to prove that W is a subspace. Okay. So it's not too bad. It follows the exact same steps as above. So just show that it's non-empty, show that it's closed under addition, show that it's closed under scalar multiplication. Once you show that, then you have shown that it's a subspace. Okay, so we're just going to go through a few more definitions, and then we're going to end today's lecture and then continue with examples just to illustrate those definitions tomorrow. Okay, so the first definition is a linear combination. Okay, so a linear combination is an expression constructed from a set so a set of vectors by multiplying each vector by a scalar. Okay, so we do our scalar multiplication on each of the vectors by different scalars and adding the results. Okay, so what is this? So we have some set of vectors, let's say v1 to vn. We scalar multiply them, and then we add the results together. So the final result will be something like alpha 1 v1 plus alpha 2 v2 plus dot 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 plus alpha n vn. Now, since at each step we're doing scalar multiplication, which produces a vector, and then we're adding vectors together, which produces another vector, this whole result is again a vector from the vector space. Okay, so this is a linear combination. Later on, we will talk more about this term here, linear. Okay, so this idea of linear is very important in vector spaces and linear algebra in general, and we will see the importance later on. Okay, so that's a linear combination. The next definition is the span. So the span, also called linear span, again, this word linear. Okay, so the span or linear span is the set of all possible linear combinations of a given set of vectors. Okay, so given a particular set of vectors, okay, so it can be any sets of vectors from a vector space V. The span is the set of all possible linear combinations. So we can write it as the span of a given set. So let's say V1 up to Vn is equal to the set of all linear combinations. So that will be something like alpha 1 V1 up to alpha n Vn, where these alpha r's are complex numbers. Okay, so all possible constructions like that, we call that the span of the set. Okay, another homework problem. Yeah, so all these homework problems that we go through at the week, they will be due at the end of the week. Yeah, so we can go through all of them at the end. Okay, so but do try them out now before we go through the solutions on Friday. Okay, so the homework is prove that the span V1 up to Vn is a vector subspace of V. Okay, so show that it is a vector subspace. Okay, another definition. Okay, so we'll cover all the definitions now, just to get them out of the way, and then we will look at why these definitions are important and all the examples in the next lecture. Okay, so next definition, a set of vectors G, which is a subset of V. Okay, so it doesn't have to be a vector subspace, just a subset, is called a generating set. Called a generating set if the span of G is equal to the vector space V. In other words, any element in V can be represented as a linear combination in G. So just a note. So any vector in V can be represented by a linear combination in the span of G. Okay, so that's why we call it the span, because G, the span of G will span across the whole of V. Okay, so it reaches all parts of V. Yeah, if that's the case, we call that a generating set. Okay, so we see above here that the span is a vector subspace, so it's a subset, a subset or subspace of V. Okay, and if we have this extra condition that it's equal to V, then it's a generating set. Okay, so this only happens in particular situations. So in general, it's a subspace. In particular, for this case here, it is the entire space. So it's equal to the entire space. Okay. However, this set G can have more elements than we actually need. So with taking all linear combinations, some of the vectors in G are redundant. We might not need them to span the full space. For example, if we just look at this, this case here, okay, so just going back to your Math 140 stuff, if we have three vectors in R2, for example. So we've got, let's say, a vector along here, a vector along here, and another one here. Okay, we know that we can reach any element using two of these. Okay, so remember your vector addition that you learned. We can use vector addition to reach any vector with two of them. If we have three of them, we can still reach every vector, but the third one is not really needed. Okay, so just a note here. We can reach any vector with these three, but the third one is not actually needed. Okay, so it doesn't hurt to have the third one. You can still reach all of the vectors, which means it is a generating set. Okay, we can reach all the vectors in V. However, it's more than we actually need. So to remove those unwanted vectors, we use this last definition that we'll be going through, and that's the idea of linear independency. Okay, so definition. A set of vectors, so let's say V1 to Vn again, is called linearly independent. And again, we've got this word linear, so we can see it's very important. It's called linearly independent. If we have this particular linear combination, so we have alpha 1 V1 plus dot dot dots plus alpha n Vn is equal to 0. So if this particular linear combination is only satisfied when all of these alpha terms, so alpha 1 equals up to alpha n is 0. Okay, so if that is the only solution such that this linear combination is equal to 0, then we say that they are linearly independent. Okay, another way of phrasing this is that out of the set of vectors, we can't write one of the vectors as a linear combination of the others. So we can't write one of the vectors as a linear combination of the others. Okay, so they are all independent of each other. If they were dependent, then one of them could be written as a linear combination of the others. In other words, that vector is dependent on those other vectors. Okay, so why is this important? Well, if one of the vectors can be written in terms of the others, well, then we don't really need it. We can throw it out. So if one or more, but we're just going to be looking at one of them for now. So if one or more of the vectors can be written in terms of the others, then it's not needed. Yeah, because if it can be written in terms of the others, well, then we can just keep the others and then throw that one away. It's not adding anything to our set. Okay, so we can throw it out. Yeah, so what we can do, if we go back to this previous definition here, if we have a generating set, G, and we know it's a generating set if it the span reaches all the vectors in the vector space. In other words, any vector can be written as a linear combination of those vectors. Okay, so in general, this G could be more than we need. Okay, it might have more vectors than we need, which means that some of those vectors are going to be dependent. And since they're dependent, we don't need them, we can throw them out. So we can throw all those vectors out from G, and we're left with a linearly independent set. Okay, and since they didn't add anything, this condition that the span is equal to the vector space, that condition is still satisfied. We call that smaller set a basis. So, definition. This pen. Okay, so definition. A basis, B, is a particular subset of B, is a subset of vectors that, number one, spans the vector space, so it's a generating set. So the span of B is equal to V. And number two, B is linearly independent. Okay, which means it is the smallest set that we can use to span the space. Because if we added elements to the spaces, then those elements would therefore be dependent. So we still have property number one where it spans the space, but since it's dependent, its property two goes away. Okay, so it's the smallest set that will span the space. Okay, so just as an example, actually, let's leave that for homework. Show that the set 0, 1, 1, 1, 0, 1, and 1, 1, 0. Sorry, this pen again. Okay, so we have the set 0, 1, 1, 1, 0, 1, and 1, 1, 0. Here, show that this set is a basis for R3. Okay, so I'll just give you some hints. So just a bit of advice on how we can solve this. So the first thing, we need to show that it spans the space. So for the set to span the space, we need to find coefficients alpha 1, alpha 2, alpha 3, such that alpha 1 times the first vector plus alpha 2 times the second vector plus alpha 3 times the third vector equals xyz for all xyz in R. In other words, we need to find particular coefficients, alpha 1, alpha 2, alpha 3, such that we can reach any vector in R3 by this linear combination. Okay, so maybe we can reach only a subset of vectors. Okay, so maybe we can't reach a particular vector. In that case, it can't be a basis because it doesn't span the space. But if we can reach all of the vectors, then it is a basis. Well, it's a generating set for now. We need to show it's linearly independent, and we can do that in this next part. So to show that the set is linearly independent, to show that the set is linearly independent, we need to show that alpha 1, 0, 1, 1 plus alpha 2, 1, 0, 1 plus alpha 3, 1, 1, 0 being equal to the 0 vector. So this can only happen. So show that this equation is only satisfied when alpha 1 is equal to alpha 2, which is equal to alpha 3, being 0. Okay, so if we can show those two here, so number 1 and number 2, if we can show those two, then it means that that set is a basis. Okay, so it's not too difficult to do. We will go through that's the solution and the solution to all the previous homework problems on Friday. Okay, and tomorrow we will go through more examples on finding the span, finding linearly independent subsets, finding bases, and so on. Okay, and then after that, I will introduce the so-called Dirac notation for vectors. Okay, so it's a slightly different notation to what we've been using here, but that is the notation we're going to carry on through to quantum mechanics. Okay, but before we get to that, please make sure that you go through your vector material from Math 140. Okay, so the additional vectors, inner products, cross products, and so on, matrices, all of that. Please make sure you know that before we get to the next section. Okay, but as always, if you have any questions, please email me. You can also visit me in my office. I should be there most of the time. Okay, I'll see you next time.